Welcome to the Explainer. Okay, I am absolutely thrilled about today's topic because honestly, we're going to reverse engineer something that sounds like it was pulled straight out of a sci-fi blockbuster. But it's actually a very real, incredibly sophisticated metamaterial. We're talking about the kinetic dissipation mechanics of open-cell aluminum matrices infused with graphene-functionalized dilatants. Yeah, I know, it's a total mouthful, but stick with me because by the end of this explainer, you're going to see exactly how a hybrid sponge of metal and smart liquid can literally stop a high-velocity impact dead in its tracks.
And to really get this, we have to start with a massive, fundamental shift in material science. Static armor? It's dead. I mean, for centuries, our entire approach to stopping kinetic energy, whether that's a speeding bullet, a vehicle crash, or flying shrapnel, has basically just been to slap a thicker, heavier, static piece of metal or ceramic in front of it. But that old paradigm is completely over. Today, we're stepping into a gritty, dynamic new reality, where materials actually fight back. They literally change their physical state of matter in microseconds just to survive.
Section 1. The metamaterial architecture, scaffolding, and core. Let's dive right in.
To really wrap our heads around how this metamaterial pulls off its magic, we have to look at how it perfectly integrates two wildly different physical phases. First up, we have the scaffolding. This is our static phase. Just imagine a highly rigid metallic sponge. It's an open-cell aluminum metal matrix composite, about 75% air, so super porous. And it is incredibly tough. It's forged from 40 micrometer aluminum powder that's mechanically alloyed with silicon carbide nanoparticles and then sintered in an ultra-pure argon atmosphere. That maximizes the strength of the struts. But here's the crazy part. The real magic is actually hiding inside the empty open pores of that sponge. That brings us to the second phase, the core. This is the dynamic phase. It's a vacuum-infused, graphene-functionalized, shear-thickening fluid. So essentially, we have this highly rigid metal skeleton perfectly infused with the phase-shifting smart liquid.
Now, what's truly fascinating here is the exact recipe of that dynamic core. Think of it like a highly engineered chemical cocktail. The liquid carrier itself is polyethylene glycol, or PEG. Floating inside that carrier, making up 60% of the weight, is a thick suspension of tiny 200-nanometer colloidal silicon nanoparticles. But notice the incredibly tiny 0.5% fraction of the recipe. That is pristine 1 to 3-layer graphene. And you know, this almost imperceptible fraction of the material is literally the master key to the whole shebang. Without that tiny sliver of graphene, the entire system totally falls apart.
Which brings us to Section 2, the absolute requirement of pristine graphene.
I really cannot overstate this point. Pristine graphene is what separates this groundbreaking material from a pile of failed laboratory experiments. The entire kinetic defense mechanism will catastrophically fail if the graphene lattice has even a single flaw. So what exactly do we mean here? Well, pristine graphene means a lattice with absolutely zero mechanical defects and zero oxygen functional groups. We can't just swap in cheaper graphene oxide or reduced graphene oxide. The absolute mechanical perfection of the basal plane isn't just a nice-to-have feature, it's a completely non-negotiable plot point for the survival of this material when it takes a hit.
And that's because that flawless lattice has to pull double duty, performing two wildly different jobs depending on what's happening. During peacetime, what we call a low shear state, we see its tribological supremacy. Basically, the perfect basal plane acts like an incredibly sleek, solid-state lubricant. It keeps those silicon nanoparticles flowing smoothly past each other, so they don't accidentally clump up. But the literal microsecond the material is subjected to violent stress, it transforms. It becomes tensile rebar. Because that pristine lattice has absolutely no microscopic fracture points, it acts as an unbreakable microscopic reinforcement, massively amplifying the yield strength of the fluid as those particles violently jam together.
Section 3. The kinetic event arc. Duality of state.
Okay, now we need to map out exactly how this material responds to kinetic energy. It operates on a strict, almost Jekyll and Hyde duality of state. On one hand, we have phase 1, which is Newtonian compliance. Under a static load, or, just slow, gradual movement, like the articulation of a robotic limb, the fluid inside the metal sponge flows completely freely. It behaves totally normally. The aluminum struts do all the heavy lifting, and the overall material stays compliant and flexible. But juxtapose that with phase 2, the high-velocity state. If a sudden ballistic impact hits, those fluid dynamics are violently interrupted. The liquid undergoes instantaneous shear jamming. In a flash, it turns into a solid.
There's actually a power law equation that governs the exact mathematical trigger for that violent transformation. Tau equals k times gamma dot to the power of n. Now, don't worry about the math too much. The key takeaway here is the variable gamma dot, which represents the shear rate. When that shear rate becomes extreme, like, say, a bullet tearing into the material, the value n becomes greater than 1. And that is the exact precise mathematical onset of the dilatant phase shift. It violently and instantly turns that liquid core completely rigid.
Moving right along to Section 4, slowing down the impact, microsecond mechanics.
Let's simulate a high-velocity ballistic strike, and I want to slow time all the way down so we can actually watch the sequence of survival unfold inside the microscopic pores of this metal sponge. Step 1. Microsecond hydroclustering. The kinetic shock wave smashes into the material. The shear force makes the silicon nanoparticles overcome their natural repulsion, and they just violently crash into that pristine graphene lattice, wedging together to form a solid state in literal microseconds. Then, Step 2. Cellular halt and internal bracing. Now, normally, a porous aluminum foam would just immediately crush inward under the force of a bullet. But here, as the metal struts just begin to bend, the fluids surrounding them instantly harden. Suddenly, those fragile metal struts are perfectly braced from all sides by a rock-solid core. Finally, Step 3, lateral energy dispersion. Because the foam literally cannot crush inward anymore, all that kinetic energy has nowhere to go but sideways. It's forced to travel outward, safely dispersing through the rigid hydroclusters and the reinforced aluminum struts.
And that leads to this absolutely crucial, game-changing result: zero backface deformation. You see, traditional body armor might stop a bullet, sure, but the back of the armor bulges wildly inward, causing massive blunt force trauma to the person wearing it. But by forcing that intense kinetic shockwave to dissipate laterally across the macrostructure rather than punching deep into it, this metamaterial completely eliminates that deep, localized penetration. The energy goes wide, not deep.
Section 5. Thermal wicking and recovery.
But wait, there is a massive, fatal flaw in traditional liquid armors, and that is intense friction heat. Think about it. When millions of nanoparticles slam into each other in a fraction of a microsecond, they generate insane localized heat. Enough heat to completely vaporize the carrier fluid. It essentially cooks the liquid armor from the inside out, totally destroying it after a single hit. And this is exactly where pristine graphene proves it is absolutely vital yet again. With a jaw-dropping thermal conductivity of greater than 3,000 watts per meter Kelvin, it acts as a molecular superhighway. It instantly grabs that intense, localized friction heat and pulls it away.
We can actually model this brilliant thermal dissipation using Fourier's law of heat conduction. The heat flux density, Q, is governed by the temperature gradient in that incredibly high thermal conductivity of the graphene, which is K. Basically, this perfectly illustrates how the graphene serves as the ultimate bridge. It aggressively wicks the intense heat right away from the jammed nanoparticles and dumps it directly into the massive macroscopic aluminum scaffolding. Let's quickly summarize this beautifully elegant recovery sequence. First, the graphene instantly wicks the localized heat away from the hydroclusters. Second, the entire aluminum block steps up, acting as a massive heat sink that eagerly absorbs all that thermal energy. Third, because the heat is sucked away so incredibly fast, the molecular integrity of the PEG carrier liquid is completely preserved. No boiling, no vaporizing. And finally, because it survived the heat spike, the core simply relaxes back into its compliant, flexible, phase-I Newtonian state just mere milliseconds after the impact. It cools itself instantly and is perfectly ready for the very next strike.
Honestly, it is a staggering feat of materials science. We've literally taken a porous metal sponge, filled it with a fluid that turns into unbreakable rebar under pressure, and used pristine graphene to perfectly solve both the mechanical and thermal limitations of the entire system. So I want to leave you with this provocative thought as we wrap up our explainer today. If a liquid can be engineered to actively brace metal in microseconds, surviving the most violent ballistic impacts without losing its form, what else in our physical world, from the vehicles we drive to the critical infrastructure we build, is just waiting to be completely rewritten by extreme kinetic forces? Think about it. Thanks for joining me on this explainer, and keep questioning the world around you.